Okay, now what we want to look at now is the first test where we can determine if a series converges, an infinite series converges. Now, this test is not going to tell us what the series converges to. It's just going to tell us if it does converge to something or if it diverges. And it's called the integral test. Now, think about a function. Think about a function, and we have this property. Okay. So we have some function here. Now, let me explain what this is. Let's suppose I have a function that is f of x is equal to like 1 over x squared. Well, this notation here, what I'm trying to say is that the series would be 1 over n squared. Right? In other words, f of n is equal to 1 over n squared. Because this is what we generally use n or k when we're talking about a series instead of x. X has the connotation of being continuous. So here's what we're going to say. We're going to assume that we have a function that is positive. The terms of the function, the terms of the sequence is positive. So these terms are positive. And that out to a certain point, once we get past a certain point, the function is continually decreasing. It's decreasing always as we go out. So let me draw you a picture of what I'm talking about. Let's suppose that we have a function and all the terms are positive. Okay? So maybe it looks like this. Okay? All the terms are positive, and maybe I'll start over here at 1. Okay? 1. And now notice, past this 1, the function is always positive and it's always decreasing. Okay? So this is what we're saying, that the function is always decreasing. Now, really, this theorem, this integral test, will work as long as there's some point out here where you start to have every term is getting smaller than the previous. But we're just going to say, okay, let's suppose that we have this function and it's always decreasing. And let's just go out a little ways here. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So let's just go out a little ways. And what I want to do, I'm going to try to convince you that this theorem, or that I want to try to convince you of a way to use the integral to determine if a series converges or not. So if we go over here, and this is something you did in Cal 1. When you were first introduced to the integral, you remember you went and did these little rectangles, right? Now here's what we know. And notice I've chosen the width of these rectangles to be 1. Now, if you look at a sum, let's suppose we're going from 1 to 9, and we've got this function. Okay. Now, this function here is going to be greater than this. It's going to be greater than, well, actually, let me go back the other way, the way I've drawn this. This is going to be less than, would you agree with this? This is less than f of 1 times 1, f of 2 times 2. In other words, the area of these rectangles is greater than the area bounded by the curve and the axis, right? So we could say this, that this is, x sub I, and I goes from 1 to 8, right? See? Because 8 is this last rectangle, right? The height of the last rectangle is f of 8, okay? That's definitely true. And in fact, I could do 9 minus 1, which is, it'd be easier for me to transition over in a minute because I'm going to be more general. But let's suppose then that we go the other way. And let's suppose I start over here and do a right sum. Okay, so the right sum is in blue, right? See? So I've got these blue rectangles. Okay? Now, the integral is bigger than that, right? In other words, these rectangles right here, if I calculate the area of these, it's going to be less than the area under that curve, definitely, right? So let me do this. This is greater than the integral, not the integral, but the sum. Then the sum, what does the sum start with? 2? So I equals 2 to what? 9? Yeah, 9. Okay. And this is f of x sub I. Okay, does everybody agree with that? That this integral is somewhere between these values. Now what I want to do, I want to change this a little bit. And then, now notice this, that if you think about this right here, if I wanted to write that as a partial sum, it wouldn't be the nth partial sum, would it? Think about the nth partial sum. The nth partial sum is f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5, right? That would be like the fifth partial sum would be f of 1, f of 2, f of 3, f of 4. But I'm leaving off this part right here, right? So what would this be? On the left-hand side, what can I write that? If I wanted to write that as like the ninth partial sum, what would it be? It would be the ninth partial sum, but I would need to subtract off something, right? Yeah, I would need to subtract off f of 1. Do y'all see that? Okay, so this is less than, so 1 to 9, f of x dx. Now what about this one over here? If I wanted to write this as some partial sum, what would it be? If I'm going, what is this one? Remember, it's this one over here, so what would it be? It'd be 8, right? Do y'all see that? Any questions about that? Now, here I went from 1 to 9, but let's suppose that I'm going from 1 to n. Okay, if I'm going from 1 to n, how would this be changed? This left one, I would have n minus what? Yeah, it'd be like a of 1, right? And what would this one be? And now this is 1 to, let's do infinity. And what I'm going to do is let me go n. Okay, n. Okay, so what would this one be over here? This s sub 8. N minus 1, right? Okay, does everybody see that? Okay, now, let's think about this. What if the series, there is a limit to the nth partial sum? In other words, what if there is a limit to this thing right here? Okay. Oh, or let's do this. Let's do this. What if this right here, let's suppose we've got infinity up here, and let's suppose, or let's do this. Let's do the limit as n goes to infinity of s sub n minus a1. What is that going, in other words, for whatever choice of n we choose, since this right here is always bigger than this, if this integral converges, if it has a value, if it converges to something, what does that tell you about this right here? It's going to be bounded, right? It's bounded and monotonic, so that tells you that your series is going to converge, right? So if this thing converges, the integral from 1 to infinity, if this integral is always bigger than this, and this integral converges, then that series has to converge, right? Now, on the other hand, what if this integral diverges? What does that tell you about the series? Yeah. So, you know, the integral is between these two. It's bigger than this one, less than this one. So you can kind of use this and say, well, if the integral converges, it's bigger than this, then this has to converge. If the integral diverges and it's smaller than this, then the series has to diverge. Okay? So let's look at an example of how we would use this. Let's suppose that we've got this well, let's look at a series. Let's suppose we've got 1 over n squared, and n goes from 1 to infinity. Now, we set some requirements to use the integral test. We said this series, every term of the series has to be positive, and it has to be decreasing. Okay? Well, let's see if this meets the requirements. So I've got this function here, and yeah, you can see that this thing is decreasing, right? Obviously. And it's always positive. One of the things you can do to determine if it's always decreasing, remember, is you can take the derivative. Well, that's to be a -3, right? Would that be it? And that's the derivative? Well, this is x to the -2, right? Oh, yeah, +3 down there. +3. Yeah, +3. Okay, so that's the derivative, right? Now, if you look at this, you can see, yeah, this is always negative. No matter what value for x you choose, this is you know, in the positive direction. This is always going to be negative. X is 1, x is 2, x is 3. So that tells us that the function is always decreasing. Okay? So this does meet the requirements to use the integral test. Now here's what the integral test does. What we do is we write this as 1 over x squared, and I'm going to go from 1 to infinity. So what I'm going to do is I'm going to evaluate that integral and see if it converges. Now this is going to actually give me a value if it converges. That's not the value of the series. That's not what the series converges to. That just tells me the series converges. So, okay, so here's what I'm going to do. I'm going to go ahead and go through the process that we use when we're evaluating improper integral. Okay. And now I get the antiderivative. So I've got the limit as b goes to infinity of, let's see here, this is going to be -1 over x, right? Okay. Now, let's see what happens. If we plug in, we've got the limit as b goes to infinity of -1 over b minus the limit as b goes to infinity of -1 over 1. Well, this goes to 0, right? So this definitely converges, right? What's it going to be? 1? Converge to 1? Okay. Now, what we say then is, since that converges, since that integral converges, then this converges by the integral test. I'll just put INT. Okay? It converges by integral test. And then we're done. We don't need to do anything more with it. Okay? Any questions about that? Now, so this series converges. Now let's look at a different one here. Let's suppose that we've got 1 over n goes from 1 to infinity. So we're going to use the integral test, and once again, you can see this series is always decreasing. Every term is smaller than the one previous, and they're all positive. So we look at this. We go 1 over x, 1 to b, the limit as b goes to infinity. So this is going to be the limit as b goes to infinity of the natural log of b. No, natural log of x, I'm sorry. And it goes from 1 to b. Now, notice I didn't use the absolute value of x. I just use x because we're starting at 1 and going in the positive direction, so you're not going to have any negative values that you're plugging in. So I just did natural log of x. Now, if you go ahead and evaluate this, the limit as b goes to infinity of log b minus log 1, you see that definitely diverges. Because log b it blows up. It goes to infinity as b goes to infinity. It gets there slowly, but it goes, right? So this diverges. Okay? And since it diverges, we know the series diverges. So we say this. We say 1 over n as n goes from 1 to infinity diverges by the nth test. We use that notation, the integral test. Okay? So you can see what we're going to have to do is we're going to have to integrate. Okay? Let's look at one more. Let's suppose that we've got log x, summation. Let's suppose that we've got the summation of log n over n. And n goes from 1 to infinity. What do you think about that one? Well, the first thing you think about is the nth term test, right? You think about the nth term test first before you do the integral test. Now, this passes the nth term test, right? The limit of log n over n is 0. Okay? So we can't rule out that it might converge. Now, I'm wondering, though, if this thing is continually decreasing. All the terms in here are positive, but I'm wondering, is this integral continually decreasing? Because if it is, I'm going to think, okay, I can use the integral test. So let's see. We've got f of x is equal to log x over x. Now let me differentiate. Derivative of the top is 1 over x times the bottom, right? Minus the derivative of the bottom times the top. Okay? Now let's see what we've got here. We've got 1 minus log x over x squared. Now the bottom is always positive. The question is, what is the function overall? Is it decreasing? It's decreasing as long as x is bigger than e, right? Okay, so if you put an e in place of x, you get 1 minus 1 up top. But then if you go past that, you're going to get negative numbers, right? Okay, do y'all see that? So as long as you are past e, this thing is decreasing. For that reason, we can go ahead and set up our integral. From 1 to b, the limit as b goes to infinity of log x over x. So when you decide to work with the integral, go ahead and change from n to x. Okay? Because n denotes discrete values, whereas we're not going to have that with this integral. We're going to have continuous values for x. Now, what do you think? How would we integrate this? Yeah, maybe you can let u be log x, then du is 1 over x dx. And then you have this. If you have, well, it looks like we just have u du, right? Which is going to be 1/2 u squared. And I'm not going to put the plus c. I just want it, the antiderivative. Okay. Do y'all see what I did there? Okay. Now, let me go ahead and write what we've got. We've got the limit is b goes to infinity of 1/2 log x squared, right? Is that right? Everything's good? Does that converge or diverge? What do you think? Log b as b goes to infinity. What does it do? Huh? Looks like it's going to diverge, right? Yeah. I mean, log x diverges as x goes to infinity. Well, log x squared will diverge, right? So this diverges. So we say our sum diverges as well. Our series diverges. Okay? Any questions about that?